Finish up chapter 16 solutions. Move on to 17, which deals with acid and bases. We leave off around here. You guys just all seeing this? All right, let's talk about solution composition next. Solution composition, you usually express it in terms of percent by mass or percent by volume. And so percent by mass is just the equal to the mass of the component A over the total mass times 100%. So that's what's shown here. Percent concentrated by mass is mass of component A for the total mass. We can have more than one solute. There could be multiple solutes. And so if there's only one solute, we say mass of solute over the mass of solution. The mass of the solution is the total. Since the solution consists of both the solute plus the solvent here. So the mass of solution equals the mass of solute. If we multiply by 100%, we get percent composition. Sometimes the composition is very small. And so multiplying by 100 doesn't really get it to a decent number. Sometimes it's really too small. In other words, this mass ratio is so small, it's better to multiply by a million. If we multiply by a million, do you know what we get? We don't get a percent. We get parts per million. Or we multiply it by a billion. And so one thing they should do is they should put percent here. So this converts it into percent. Multiplying it by a million, we put a million pp in. Billion, B, etc. Mass percent. Well, the solution consists of everything. So everything is the solute plus the solvent. That's what we have here. Solute plus solvent. When 125 grams of a solution was evaporated to dryness, 42.3 grams of solute was recovered. What was the percentage concentration of the solution by mass? So in this solution, they had 42.3 grams of solute over a total 125 grams total. And then times 100%. So 42.3 grams of solute over 125 grams total solution. Put the units in there. And you get 33.8% solute. So about 1/3 of the mass of that is solute. All right, this is a different problem here. You're to prepare 2.50 times 10 squared, or 250 grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? And so first, what is 7.00% by mass sodium carbonate? Well, what that means is we have 7.00 grams out of 100 grams of what? So this is why we should probably put some units on here. Because in the numerator it's going to be solute over solution in the denominator. So in this case it's 7.00 grams of solute. The solute is pure sodium carbonate. In 100 grams of sodium carbonate solution. Sodium carbonate solution would be the mixture here. If we multiply this by 100%, then we get the percentage by mass. But this ratio, this mass ratio, is what we use for conversion factor, as a conversion factor. And so if I have 100 grams, I need 7 grams of sodium carbonate. If I have 200 grams of solution, how much sodium carbonate will I need? 100 grams requires 7 grams. 200 grams of solution would require 14 grams. 250 grams would require what? Well, 50 grams would require half that, so that's 3.5 grams. And so 250 would be 17.5 grams of sodium carbonate. So this one we could do in our head pretty much. Don't have to, but we could do it. 17.5 grams of sodium carbonate. Other calculations are more difficult because the number, it's not so simple. Like this one was simple because it was just 250 grams, but it might not be. And so we'd want to set it up dimensionally like this, using dimensional analysis. You're given 250 grams of solution. There's 7 grams of sodium carbonate for every 100 grams of solution. Grams of solution cancels, that gives us grams of sodium carbonate, 7.5 grams. What else are they asking for? And what volume in milliliters of water do you use? They give us the density of water is 1.00 grams per milliliter. So in other words, we have 250 grams of solution, sodium carbonate solution. This sodium carbonate solution consists of pure sodium carbonate, of which we have 17.5 grams of pure sodium carbonate, which is a solid, plus the solvent. The solvent in this case is water. There's just 2 things in this mixture, sodium carbonate and water. And so how many grams of water do we have here? Well, we have 250 grams total. That's going to be 17.5 grams plus X grams of water. How many grams would that be? Can you do this calculation in your head? $232.5. You say 232.5. In other words, we're taking 250 grams minus the 17.5 grams will give us the grams of water. We calculate 232.5. Your book rounds it to 233. 233 grams. If we use 233 grams of water plus 17.5 grams of sodium carbonate, we're going to get a little more than the 250 grams they're asking for. A half gram more. That's in grams, but I forgot, they want it in milliliters. And so if we have 233 grams of water, how many milliliters is that? It's the same, 233 milliliters, because the density is 1.00 or 1.0. It's only when we get to like 4 sig figs that we start worrying that they aren't the same. The 3 sig figs or 2 sig figs are going to be the same. The mass of water and the volume of water. All right, percent by mass we can use for any type of solution. Liquid solutions, solid solutions, gaseous solutions. Can use them. But we don't just use percent by mass, we also have percent by volume. Like, for example, some alcohol solutions are percent by volume. Like it might be 50% alcohol by volume. That means it's 50% water, 50% alcohol by volume. And so percent by volume, this could be for anything. Percent by mass, solid, liquid, gas. Percent by volume, well, solids are a bit of a pain, to do percent by volume. And so typically percent by volume is for liquid and gaseous solutions. Air. air is 80% by volume. Nitrogen. It's easy. Percent by mass, well, nitrogen is light compared to oxygen. The percent by mass is a little less. And so percent by volume is common as well. ppm is common, ppb is common. Those are all different ways of expressing the composition of liquid solutions. The most common, though, is this one, molarity. We already dealt with molarity a little bit in the titration file, but molarity is defined as the moles of solute per liter of solution. Moles of solute per liter of solution. It's given the symbol capital M. And the reason why this one's one of the most common ways of expressing solution composition is because it works so nicely in stoichiometry. Moles per liter. Calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide in water and diluting it to 1.00 times 10 squared milliliters to 100 milliliters. So if we take 15 grams of sodium hydroxide and dilute it to 100 milliliters, what is the molarity? Well, the molarity of sodium hydroxide is equal to the moles of sodium hydroxide per liter of sodium hydroxide solution. And so, well, notice that this is a little bit different. It says in water, dissolving it in water and diluting it to 100 milliliters. They aren't telling us how many milliliters of water they added. Does it say how many milliliters of water they're adding in this mixture? No. If we look at the previous problem, did they say how many milliliters of water they're adding? Yeah. They're adding 233 milliliters. But when you take a solid, are the volumes additive? Let's say you took a milliliter of salt crystals and it added that to a milliliter of water. Are you going to get 2 milliliters of a solution? Or let's say you took 3 milliliters of sugar cubes and it added that to 100 milliliters of coffee. Are you going to get 103 milliliters of coffee? No, it's weird how things add up because when you break apart the crystals, the volume changes. Because crystals aren't using the spaces maybe more efficiently or less efficiently than the liquid. And so when we take this sodium hydroxide, actually I don't know how much water we're going to need. This is a little different because we know how much water we're going to need because we weigh it, by the mass. This one's going to be different. And so what they're saying is they don't know how much water they're going to use, but what they do know is they need enough to make 100 milliliters. So they're just going to keep adding until it hits 100 milliliters and stop. And so the volume of the solution here is 100 milliliters, but we have to convert it to liters. So 100 milliliters is equivalent to 0.100 liters. And so we have 0.100 liters of sodium hydroxide solution. And that goes here. And so we have half of the molarity done. The other half is the molarity of the moles. So, well, we just do a gram to mole conversion. So if we have 15 grams of pure sodium hydroxide, and we know it's molar mass, we can just convert that into moles of sodium hydroxide. Well, let's take a look at the molar mass of sodium hydroxide is 40.00 grams per mole. So we can do that here. This is just going to be 15 grams of sodium hydroxide. This is pure sodium hydroxide. Every mole of pure sodium hydroxide weighs 40.00 grams. it's going to give us, I don't want to do an intermediate round off, so I'm going to carry an extra digit. So it's 15 divided by 40, 0.375. So this gives us 0.375 moles of sodium hydroxide. All right, then we plug it all in here. 0.375 divided by 0.1 gives us 3.75 moles per liter or molar sodium hydroxide. In other words, this is going to come out to 3.8 molar sodium hydroxide. So first they calculated the moles of sodium hydroxide, and then they calculated the liters of sodium hydroxide solution, and then just took the moles divided by the liters to get the molarity. So there are 3.8 molar sodium hydroxide. Okay, molarity is the most common, actually. More common than percent by mass. Molality is not. Molality, we're just going to use molality for two types of calculations. One is called freezing point depression, the other is called boiling point elevation. And we're going to talk about those a little bit later. Otherwise, we don't use it much. It's not as convenient. Because here, it's moles of solute per kilogram of solvent. So if I had sugar water, I'd have to know how many, kilograms of sugar and how many kilograms of water I have. Versus molarity, I just need to know how many liters of sugar water I have. Well, it's a lot easier to know how many liters than how many kilograms of sugar and how many kilograms of water. And so molality isn't as convenient. But one thing molality does have a big advantage over molarity is that it's temperature independent. Molarities change with temperature. The reason they change with temperature is because liquids expand with temperature and contract. If a liquid gets hot, it typically expands. If it cools down, it contracts. So if the volume expands, then the molarity goes down, or the molarity goes up. The volume contracts. And so the molarity changes with temperature. However, the molality will not, because the kilograms don't change. If you have a kilogram of metal, whether it's room temperature or hotter, you aren't losing any atoms. So as long as you don't lose any atoms, the number of kilograms should stay the same, since it's just a measure of the quantity of matter. And so molality we aren't really going to use much. In fact, I'm going to skip this question here. We'll do a molality calculation later. Normality is even rarer. You'd be hard pressed to find somebody who uses normality, unless they work in an analytical chemistry lab. If you work in an analytical chemistry, then normality is kind of convenient. It just shortens the stoichiometry a little bit. Maybe. So skip normality. So here's a summary of the solution concentrations. Number one, molarity. This is the most frequently used. Definition is moles of solute per liter of solution. Molarity. Percentage by mass or percentage by volume is the next. Molality, not really. And normality, never. Usually when we buy chemicals, we buy concentrated chemicals to save money that way. If you buy the concentrated stuff and dilute it, it's cheaper than buying the pre-diluted stuff. And so this goes for like soaps. You might buy the concentrated soap and dilute it yourself. It's a bit of work. It's a bit of a hassle to dilute it, but it could be worth it in amount of money you save. Yeah. Some people don't want to hassle with diluting, like bleach. You know, some bleach solutions they'll just buy pre-diluted. The bleach, you know, has a pretty nasty odor to it, burns, and so diluting it is not that fun. But other things are easy to dilute, like simple green. Simple green's easy to dilute because the green color just fades, so you don't have to do too much. But some things you can't tell, you know, how much you diluted it by. So we have this. This is the solution-dilution equation. In lab, we typically use this in one of two ways. One way is just to figure out the diluted concentration or dilution that we need. And so we typically rearrange that like this. The molarity of the dilute solution is equal to the volume of the concentrated solution over the volume of the dilute solution times the molarity of the concentrated solution. Like that. This factor here, this is called the dilution factor. Dilution factor. Where does this equation come from? This equation comes from this. What are the units of molarity? Moles per liter. What's the unit of volume? Liter. So moles per liter times liter gives us moles. And so the moles at the beginning will equal the moles at the end. The number of moles don't change when we do solution dilution. We can see that illustrated in this slide here. If we look at the solute, the moles of solute don't change. So here we have 5 solute particles. This is concentrated. Then we're going to add more solvent and make it dilute. This is dilute, but it still has the same 5 solute particles, just the volume is going to be bigger. And so this would be same number of moles before and after. So that's where that equation comes from. This dilution factor comes from this. The dilution factor is looking at this. We start off with one part, and then we end up with how many parts? Okay, if this is one part, then it looks like we end up with 1, 2, 3 parts. So if we start off with one part and end up with 3 parts, you know what that's called? That's called a 1-to-3 dilution. A 1-to-3 dilution. And so 1 part being diluted to 3 parts gives us a dilution factor of 1/3. The dilution factor of 1/3 means the concentration should be 1/3 the original concentration. And so whatever this concentration is, I expect this concentration to be 1/3 that. This is a 1-to-3 dilution. We could have a 1-to-2 dilution. Let's say we take 1 part and then dilute it to 2 parts. That would be a 1-to-2 dilution. If we did a 1-to-2 dilution, what would the dilution factor be? 1/2. And so we'd have half the concentration. So this is one way of using this equation. So let's see. This is how we do it in practice. In practice, you don't measure how much water. You just fill it until you hit the right volume. Well, these are called volumetric flasks. These volumetric flasks are quite expensive, and the volumetric flasks are made to measure only one volume. And so this one's called a 100.0. It's actually a 100.00 milliliter flask. There's a line etched in the neck here, and if you fill it just to that line, that's 100.00 milliliters. If you overshoot that line, then you have too much. If you undershoot it, you have too little, but we don't know how much is too much or how much is too little because it's not marked. There's only one marking. So here we have 100 milliliters of concentrated stuff. So 100 milliliters of the concentrated stuff. The concentrated stuff is not that concentrated, it's 0.100 molar. It's not that concentrated, but. So they're going to take the concentrated stuff and put it into the flask. They're going to rinse out this flask to make sure every drop is transferred over. So once they get all the concentrated solution transferred over here, then they're going to add water to fill it up to the mark. Where's the mark? Well, this is a 1,000 milliliter flask. 1,000 milliliter flask. And so they'll just keep adding water until it hits the line right here. If they put in 1 drop too much, you know what they have to do? Or 2 drops too much. 1 drop too much, you know what you're supposed to do? If you overshoot this by 1 drop, you don't know what the volume of that drop is. And so what you have to do is you dump it and start over again. If you overshoot, it's a waste. And so you're very careful not to overshoot this line, because then we don't know how much the volume is. It's not marked. But anyway, if we hit it right on the line, then we're good. We get a 100 to 1,000 dilution. A 100 to 1,000 dilution, what's that dilution factor? Well, it's going to be 100, which is the volume to begin with, and the final volume is 1,000, so it's a 1 to 10 dilution. It's a 1 to 10 dilution, what's the concentration going to be over here? Well, if the concentration over here was 0.1, then this concentration will be 0.01. And so it's 0.01 hundred molar here. And it's 0.1 hundred molar there. Does that make sense? And so that's a 1 to 10 dilution. How much water do they add? They don't keep track. How much water? They added enough water to hit the 1 liter mark. That's how much water they added. Nobody ever bothers calculating what volume of water or how many grams of water. They just start filling it up until it gets right there. That's different than the first problem we looked at. All right, how many milliliters of commercial hydrochloric acid, which is 11.6 molar, should you use to prepare 5.50 liters of 0.500 molar hydrochloric acid? So when we buy hydrochloric acid, we buy the concentrated stuff. It's a lot cheaper in the long run to buy the concentrated stuff and then just dilute it. So the concentrated stuff, that's commercial, is 11.6 molar. And so we have lots. This is called stock solution. You might have stock solutions for soups. You know, how much stock solution should you use in a soup? Well, it depends on how concentrated that stock solution is and how dilute you want the soup to be. And so we should have lots of 11.6 molar stock solution. What we're going to use is we're just going to use a little bit of this stock solution because what we want to make is 5.5 liters, in other words, 5.50 liters of 0.500 molar HCl. And so what do we know here? Well, we know that this is MC, the molarity of the concentrated. We know that this is V sub D, which is the volume of the dilute, M sub D, which is the volume of the concentrated, or molarity of the concentrated, sorry. Or not molarity of the concentrated, molarity of the dilute. So what's missing? What's missing is the volume, you know? What or how much of this solution should I take? So this is going to be the volume of the concentrated. So the volume of the concentrated is equal to the molarity of the dilute divided by the molarity of the concentrated times the volume of the dilute. And so the molarity of the dilute is 0.500 molar. The molarity of the concentrated is 11.6 molar times the volume of the dilute, which is 5.50 liters. Let's see what I get. 0.5 times 5.5 divided by 11.6. 0.2370 liters. 2370 liters which is equivalent to 237 milliliters. And so I just need 237 milliliters of the concentrated stuff, dump it into this container, and then fill it up to the 5.5 liter mark. And I should have the solution that I want. I said molarity is most convenient for stoichiometry. And so let's take a look at using molarity in stoichiometry next. Calculate the volume in milliliters of 0.842 molar sodium hydroxide required to precipitate as copper 2 hydroxide. All of the copper ions and 30.0 milliliters of 0.635 molar copper 2 sulfate. All right, so why don't you give this a go here and then work on this for a little bit. Come back, take a look at it.